Okay, so we're going to start with just a simple example, just a simple derivative to take, and maybe try to interpret the meaning of the object that we find. So the function that we're talking about right now is 2 cosine t sine t t. And so the derivative, remember, of that is just derivative of each entry. So this is negative 2 sine t, cosine t, and 1. And maybe now I'll just make a general comment, not necessarily specific to this example, but in general, what does the derivative tell us? R prime of t gives a sense of changes, rates of change, in the x, y, and z directions. Right? Because literally R prime of t is equal to dx dt, dy dt, and dz dt. If you think way back to Calculus 1, this means that a small bump in t causes x to change by dx dt. A small bump in the in the t direction causes a point to move dy dt in the y direction, and a small bump in my t values causes z to change as dz dt. Really, actually, this is giving us a direction. Small bumps in t, so for small bumps in t, R prime of t gives sort of the instantaneous direction. In fact, it's the direction of the tangent to the curve. In other words, if my point was moving r of t, I had some particle that was moving and its position could be given to me by r of t at any point t, then let's even just draw this. If I had some particle that was moving through space, and I asked you at t equals, say t equals a, what's going on, then the derivative would be the direction that this particle is going. It's the instantaneous rate of change of each of those components. It gives the direction that the particle is going in tangentially. And so, I mean, if you wanted to actually plug in some points, we could look at r prime, say, of pi over 2, for example, is negative 2, 0, and 1. And so that implies that the tangent line at t equals pi over 2 has direction vector negative 2, 0, and 1. That's because a small change in t yields a relative change negative 2 times that small change for x, change of 0 in the y direction, and change of 1 in the z direction.